So I'll go through the solution with you guys, and then I'll collect them. All right. So let's see here. Let's start with finding the intervals of increase and decrease. So what's df dx here? We have what? E to the minus x squared, right? Times the derivative with respect to x of minus x squared by the chain rule. So the derivative is minus 2x e to the minus x squared, right? Now, when can that be 0? Can the exponential ever be 0? I mean, the answer is no, right? So the only way that df dx could be 0 is if this x is 0, right? So x equals to 0 is the only critical number, right? So as we make our sign chart for df dx, we only have to think about 0, right? And so if you plug in like a positive number, what do you get? You get df dx is what? Like plug in 1, what happens? I get minus 2 e to the minus 1, right? So if we plug in 1, we get a negative number. If we plug in minus 1, we get a positive number, right? So you can see that the sign chart here looks like this. So this shows me that thus f increasing on minus infinity to 0, f is decreasing on 0 to infinity. All right, so that's the answer to the first question I asked, right? That's where the derivative is positive, that's where the derivative is negative. Think so? Any questions so far? Now, how about concave up, concave down? Now we need to do what? We need to calculate the second derivative, right? So what's the trouble there? It's not really trouble necessarily, but something to think about. So f prime prime of x is d dx of what? Of minus 2x e to the minus x squared. So I just looked through everybody's mission 5, and like definitely you guys have some understanding, right? But there's some things missing. Now you guys turned that in a couple days ago, right? So maybe you understand more now. But I think everybody here still needs to do more work on like basic differentiation, and that's something you want to like have complete ownership of before you leave this course, right? Because the differentiation, it never kind of goes away, and it's like always something in calculus. Every course, every step of the story past this point, like differentiation is important. But I think everybody here has made good progress towards that. It's just you still have more work to do. And I haven't been super critical in my grading of the homework. I just kind of like put some X's where you're missing things, and if I see something, I say something. But what you should do is you should look through my solution and see if, you know, problem by problem, if what you did matches or doesn't, you know. And if it doesn't match, you should ask yourself the question, was I right and he just did it a different way or whatever? And if you can't reconcile my solution to your work, maybe you should come talk to me in office hours or something like that. Anyway, so what I'm trying to say is I'm probably too generous in my grading on your homework. Not super critical there. Now, ddx of this, so I have what? This is a product rule, right? So I can pull the minus 2 out, and I've got 2 minus 2 dx dx, e to the minus x squared minus 2x ddx. Does that make sense? And then we have to do the chain rule on this guy, right? So this works out to minus 2x e to the minus x squared once more. And so lo and behold, we got minus 2 e to the minus x squared. Minus 2x times minus 2x gives me a plus 4x squared e to the minus x squared, right? And can we factor anything out? I think I could, 2, maybe e to the minus x squared, right? So I've got 2 e to the minus x squared times minus 1 plus 2x squared, I suppose. Now, I think that's easier to think about if we just factor the other 2 out as well. You know, this is 4 e to the minus x squared times x squared minus 1/2, right? Which what? Where's this 4 coming from? Oh, I factored 2 out of this. So if you pull 2 out, that makes that minus 1 into 1/2. Right? Or you could just go back up to here and just factor 4 out directly if you want. Factor 4 out of the x squared, then I have to divide by 2 here to get a 4, you know. But bottom line is this is what? This is 4 e to the minus x squared, x minus 1 over the square root of 2, x plus 1 over the square root of 2, right? And so you can see that the place where the second derivative is 0, right, potential inflection points, as we say, are either 1 over root 2 or minus 1 over root 2. So I can draw my number line for the second derivative. I can put minus 1 over root 2, 1 over root 2 over here, and then I can think about plugging in some points. Let's see here. If I plug in, like, 1 is larger than both of these, right? So it's going to be positive if I plug in 1, right? What happens if I plug in 0? 0, I would have pick whichever formula you like best. I kind of like this one. I don't know. If I plug in 0 there, I get 4 times minus 1/2, I get minus 2. So it's negative. Yeah. And if I plug in something that's like minus 1, for example, this is negative and that's negative. So we get product of negatives is positive again. So there you go. This place is going to be concave up. This is the place that's going to be concave up. And in the middle, we got concave down. So the intervals of concave up, so f of x, y equals f of x is concave up on minus infinity to minus 1 over root 2 and 1 over root 2 to infinity. And y equals f of x is concave down on minus 1 over root 2 to 1 over root 2. All right? And so now we can graph, right? So that makes, what's that tell us? That tells us that we have an inflection point at both of these places, right? Because the concavity changes, those are inflection points. I didn't ask you to find the inflection points, but sometimes I'll say find inflection points if there are any, right? And label those explicitly on the graph. So, so here's my picture. What happens to e to the minus x squared as x gets really, really large? It goes e to the minus a really large number, right? And the same thing, if x is very, very large and negative, it's e to minus a very large number, which is, in both both cases, as x goes to plus or minus infinity, it's going to 0. So what can we say? Where's the local max? See, 0 is a local max, right? It's going up, it's going down. What is f of 0? F of 0 is 1, right? So it's there. That's a local max. And let's see here. 1 over root 2 is about, I think that's like about 0.707, so it's something like in here-ish. So these are, and if we plug in 1 over root 2, you get e to the minus 1/2. Right? E to the minus 1/2 is basically like 1 over the square root of e, which is about, I don't know exactly. I guess I could plug it into the calculator and find out. Oh, but I can't, because I forgot my calculator. Oh, but I have a phone. Oh, you tell me? Your phone is faster. So what is e to the minus 1/2? 0.606. Okay, and so like 1 over the square root of 2 is like 0.707. Is that right? 1 over root 2, is that about 0.707? Am I wrong? Okay. So it's just a little bit, something like here-ish. I mean, my graph's not exactly right, but it's something like that. And those are places where it changes from what? From concave up to concave down. So that's pretty much everything you need to make a pretty nice graph here. I mean, I'm trying, but inflection points, I do my best, but it's hard to do a really good job at it. But those are your inflection points right here. All right, and there you go. That's the graph. This is the bell curve, right? So we use this. Something like this describes probability distributions of a normal distribution, something like that. Like if you have a large enough sample size and you look at grades in a class, they'll follow a pattern like this, right? Something like, there's 68% of the grades fall in the first standard deviation. And then, if you go 5 standard deviations out, it's like 99%. And then there's stuff on the tails. Like, this function's important to probability. So-called bell curve. So there it is. So I'll collect your quiz. Thank you, thank you. Jake, you cracked me up. Here. Oh, I was like, I'm missing someone. Thank you very much. So you guys have any questions about homework? Well, mission 6 was supposed to be due Monday. I gave you guys till Wednesday to do it. At least one of you couldn't turn it in today because you just forgot it. But still working on it anyway, so if you'd like to have till Friday to work on it, that's okay, but there is another homework after that. So like I push homework back, it doesn't mean I push the homework after that back. And so I think stuff kind of is piling up. We have a test not too long from now, so you want to, try to catch up with the homework. But I'm happy to help if you have a question. Number 96, rate of change. Oh, by the way, here is the, I printed this out for you guys. So when we had that snow day, I think it was, it kind of twisted the schedule a little bit. And I redid the lab schedule. And so here's a printout. I posted it in the Blackboard, I think, about a week, 2 ago. But there it is. So like today, where are we? March 3rd, is it? So I'm supposed to talk to you guys about, optimization and closed interval method. And that is where we are. I have another probably 5 pages of examples in the notes on graphing with calculus, and I would encourage you to read those. In fact, this is one of the examples in the notes. This is like example 6.1.29 is your quiz 4 problem. Right. Let's see here. So Friday we do have a lab on Taylor, what are called Taylor polynomials. And then next week we're going to talk about L'Hopital's rule, which is actually I think easier than what we're currently doing. Like what we're doing right now has a lot of moving parts, the graphing. But anyway, you had a question, Shadrach? Yes. Number which one? Number 96. Did I post? I don't know if I posted. I don't think I posted the solution to mission 5 yet. I don't remember, but I will do that soon. I have a solution to post, so you guys can look at that once I do. Related rates. Okay, so we have 2 people on bikes start at the same place. One of the bikers starts riding directly north at 8 miles per hour. Half hour after that, the first biker started riding north. The second starts to ride directly east at a rate of 10 miles per hour. At what rate is the distance between the 2 riders increasing a half hour after the second person started riding? So it's problem 96. So what was your question? Is there something unclear about the wording? You just don't know where to start? I mean, what? The wording? Let's see here. So you can let the origin be where they start, right? Start at the same place. One of the bikers rides directly north at 8 miles per hour. So we could kind of draw a picture of that. And I'll draw the picture at the hypothetical time that we're interested in, which is what? Half hour after the second person started riding. So how long has the first person been riding at the time the question asks how the distance is increasing? After 30 plus 30 minutes, right? So if you look at that's my picture of a bike. It's kind of a sad picture, but so half hour after the first biker started, the second then started, and then the question is how fast is the distance between them increasing after that second half hour? So we're actually looking at 1 hour after the start of the whole thing, right? So I'm going to draw the picture at that time. T equal 1 hour, let's say. And I'm assuming the problem starts at t equals to 0, just to give you, And they were going at a constant rate of 10 miles per hour, right? So let's see here. What else can we say as we're making this picture? What's this distance after the 1 hour mark? If he was going 10 miles an hour for an hour? 10 miles, right. I guess that's kind of an impressive biker, right? I mean, I don't think I could go 10, I don't know. I'm not sure I could keep 10 miles an hour up for an hour. Probably not. Maybe you guys. Let's see here. Let's see here. And then the second rider starts to ride directly east. Oh, wait a minute. Did I say? I said 8. It was 8. Thank you. Thank you guys. Don't let me get away with that. So that makes this 8 miles. Thank you. Thank you. So the other one went east at 10 miles an hour, right? So we draw a picture of that. And I think I would call the I think I'm going to call this this distance y, right? And I'll call this one x, right? Now my picture is not to scale by any means, but this guy's going 10 miles an hour this way, right? And this picture is at time 1 hour. So what's that? At time 1 hour, the east moving bicyclist is only gone for a half hour, right? So how far is he gone? 0.5 times 10, what, 5 miles, right? So the biker who went east, he started biking a half hour after the first biker, right? Which means he's only been biking for 1/2 hour at the time we draw the picture. So the distance he's from the origin is 1/2 of 10 miles. It's just 5 miles, right? Does that make sense? That's 5 miles. All right. And then what's the question? The question is, at what rate is the distance between the two riders increasing at this time? So maybe I should make that in part of my picture, right? So let's say this would be the distance, right? That's the distance between them. Sometimes I call it S, sometimes I call it a D. What do you guys want? What's that? H? I call it H. You guys are funny. Okay, so what's the relation between H and X and Y? Yeah, X squared plus Y squared equals to H squared, right? Now, it's important that when you want to find the relation, which is true not just for the instant of time we're asking the question, but at all times close to that time. So it's important not to plug in the 5 and the 8 just yet. Because if you do that, then you'll just get as constant, and then you differentiate it at 0, and it's like something seems wrong. Yeah, I mean, so this is true for all time near time 1 hour. X, Y, and H, they're all functions of time, so we can differentiate this and relate the rates. Right? So this gives us that 2x dx dt plus 2y dy dt is equal to 2h times dh dt, right? And this is the quantity you're trying to find, right? But well, you can divide the 2 out, right? You can divide by 2, get rid of the 2's everywhere. You know what x is, right? You know this is 5. You know that's, 8. You know that dx dt is 10, right, in miles per hour. You know that dy dt is 8 in miles per hour, right? And you also can figure out what h is. What is h? Yeah, square root of 64 plus 25, right? Whatever that is, right? So you have everything you need to solve for dh dt, which is what the question asks for. So how is this different than the ladder problem? I mean, it's almost the same picture as the ladder sliding down the wall problem we worked the other day, right? What was the difference there? One of the differences, that is true. The ladder was not the square root of 64 plus 25 miles. That would be a long ladder. Yeah. Oh, I see. Yeah, I mean, these problems get a little bit trickier when we have some kind of asynchronous aspect to it. But if you just draw the right picture and Just put everything down that you know. You can do it. Yeah. Other question? But the other thing about the ladder that was different was that the rate of change of the y in that problem was negative because the ladder was sliding down. So like dy dt was negative, whereas both of these are positive, right? You could imagine a different problem where you started one of the bikers like out here, and then they were coming towards the origin, you know? There's all kinds of variations on this problem that can be done, but they are not really conceptually more difficult than this one. All right, well, let me show you some optimization problems here. So optimization is, really just applying calculus to word problems, looking for minimums and maximums of some given scenario. So I'll start out with a rather famous problem. So suppose you have and this one we can do in algebra, all right? But here's my example one. So suppose you have a given 400 feet of fencing, 400 feet of fence. What dimensions for a rectangular pen maximize the area? So can anybody tell me the answer without doing calculus? So, I mean, you can do this problem without calculus. You can use what's called symmetry to do this problem. See, because if you think about the fence, there's no difference between the length and the width, right? So if there's no difference between the length and the width, the solution must not respect any difference between length and width. That forces the answer to be a square, which means it's 100 by 100 by 100 by 100. Well, the dimensions 100 by 100 is what we should find. So maybe this problem isn't that interesting in the sense that it allows for a non-calculus solution, right? So to make this something that we need calculus for, I just add lava. All right, so given 400 feet of fence, what dimensions of a rectangular pen maximize the area? And you say one side has lava. So here's the picture. You've got a river of lava. Right, so that will barbecue your cows, right? Cows in here. Or whatever particular goats, whatever it is you're keeping. Now, since you have a river of lava, you don't need a fence over here, right? So what dimensions should we make for this rectangular pen, given that we don't need one side? See, now I can't use symmetry because there's a distinction between that one side versus the other two, right? So I can't just naively say, oh, it's a square. But anyway, so what you do is label. Let's call this length y. Let's call this length y, right? This length x. And then we write down equations for what we know. We know that x plus 2y is equal to what? that's the perimeter. That's the place where we're putting fence, right? Because we don't need fence on the lava side. And so that's equal to 400. And then what are we interested in? We're trying to maximize the area. What's the formula for area here? Length times width, yeah, L times W. But here, we have X, we have Y, right? So the XY, right? Very good. So we need a function of one variable though, right? So what we can do is we just solve the first equation for y, if you want to work with x. I mean, it's up to you guys. Do you want to solve this for x or for y? Solving it for x is easier, right? So this tells me that x is equal to 400 minus 2y. So I get 400 minus 2y times y. So A is 400y, 2y squared. So this is the area as a function of y. Now, so we want to optimize the area. So the optimal area is going to be the one for which we have a maximum area, right? So if you could think about graphing area versus y, we know that the maximum is going to be a critical point, right? I mean, we're not actually going to graph the area function as a function of y. That's not the point. The point is that the maximum is going to happen where dA dy equals to 0, right? We know this from our experience from our discussion of graphing and what the meaning of critical numbers are. Critical numbers are where you have maxes or mins. So if we look for critical numbers in the model, then we can just use common sense to discern whether or not it's a maximum or a minimum. Or we could calculate the second derivative. So like, what's dA dy here? We've got 400 minus 4y, right? Because we're differentiating with respect to y. What's d squared a dy squared? It's minus 4, right? See, that's less than 0. So that implies that we're going to get maximum. We'll get a maximum at the critical number. What's the critical number? All right, so we want to say dA dy equals to 0. dA dy was 400 minus 4y. That equals to 0. So that gives us 4y equals to 400. So y equals to 100. And what's x equal to? All right, we take that, plug it back up in here, and we get x equals to 200. I know that because I go back to my original picture. 100 plus 200 plus 100 gives me 400, which is how much I need a fence, right? So the dimensions, so a 200 foot by 100 foot fence maximizes area. Now, if you wanted to be grumpy with me and be like, you don't need calculus for that, I could have used symmetry. I can't really argue with you. I mean, you could also argue if the rectangular pen. So, well, I mean, you know that and that have to be equal. I guess it's not entirely obvious. Maybe I can't use symmetry. I don't see how to use symmetry to solve this problem right off, honestly. But there it is. So with a related rates problem, how does it work? You find a mathematical model for the real-world problem, and you basically differentiate it to relate the rates. Optimization problem, you find something you're interested in as a function of one of the variables involved. Then what you do is you differentiate it and set the derivative equal to 0, right? Then you can use the second derivative test or common sense to discern whether that's in fact a maximum you're interested in. Here I knew it was maximum because I actually used the second derivative test. It was negative, right? Negative second derivative. A critical number implies maximum. My next example is from electrical engineering. Are any of you guys interested in electrical engineering? No? Okay. So I'm going to skip my example 2, because to understand it, you need, circuits, a little bit of understanding of circuits, circuit analysis. And basically, all example 2 says is if you have a battery and you connect a resistor to it, to get the maximum power out of the battery, you have to match the resistance of the battery to the resistance of the load. So for a DC circuit, the maximum efficiency you can achieve is 50%, which is kind of annoying, right? This is my example 3, which I like. So here it is. The range of a projectile fired at angle theta that's that angle of inclination again, can be shown to be r equals to, that's funny. That's supposed to be, there's a typo in my notes. Sad. I know better than that. V squared sine of 2 theta over g. Where v is initial speed and g is 9.8 meters per second squared, right? So then the question is, what angle maximizes the range, and what is the max range? Okay. It's a question. What theta maximizes range? And what is that max range? So you guys might already know the answer to this question, actually, if you studied like high school physics or whatever. If you have a cannon, and we're neglecting friction here also, right? But if you have a cannon and you're neglecting friction, you want to shoot it as far as possible on a level field, what angle should you shoot it at? Yeah, you're on a level field. That matters. In fact, if the field's not level, the answer for maximum range is not what I'm about to tell you. What is our max? What's the max range? The maximum range. Yeah. That was. Oh, you understood the what. My what is kind of. My what there is a little bit sketchy. You want to guess the answer? Yeah, okay, let's work it out. 60. Here's a fun fact. If you shoot it at 60 degrees, and if you shoot it at 30 degrees, same range. Isn't that funny? You shoot it at 10 degrees and you shoot it at 80 degrees, same range, neglecting friction. Yeah. That's implicit in this formula. If you look at this formula, sine 2 theta, what's sine 2 theta's graph look like? Well, if I draw that, I'll draw the answer. Let me not do that. So to find the max range, we set dr d theta equal to 0. Dr d theta should give me the critical angle. Dr d theta equal to 0 gives critical angle, which produces max range. That's what the method of optimization says. Differentiate the model, set the derivative equal to 0, use some common sense to make sure you're, not misinterpreting things, but that will most often give you the maximum or minimum that's desired. And so that's pretty easy here. Now here, notice V and G are constant with respect to theta, right? One other big difference between related rates and the optimization problem, with related rates, we differentiated with respect to time to relate rates, right? In the first example, we differentiated with respect to y. In this example, we're going to differentiate with respect to theta. The derivative is taken with respect to whatever happens to be interesting to the problem, in this case, theta. So the v squared divided by g times the sine of 2 theta. What happens there? Well, we can pull the v squared and g out because they're constants, and then we get 2 cosine of 2 theta. 2 cosine 2 theta. The 2 because of the chain rule, right? But anyway, we set that equal to 0. And now we need to use some common sense. What range of theta should we be considering? That kind of depends on the details of the cannon, right? I mean, if the cannon can flip over, you could imagine it going from 0 to 180. But I usually think about theta ranging from 0 to 90, right? So I need to solve this for 0 less than or equal to theta less than or equal to 90 degrees. Although I think shooting the cannon at 90 degrees is ill-advised, right? You only do that once. Yeah. You guys ever seen that old Taco Bell commercial? Maybe, this is probably before your time, I don't know. There used to be this Taco Bell commercial with all these guys like celebrating New Year's or whatever in Mexico, and they're all like in this courtyard firing their guns up into the air. Like the first 20 seconds of this commercial is just them shooting. And all of a sudden towards the end of the commercial, they're like, "The bullets!" And then they all go running, and then there's just like this rain of bullets. So, but anyway, I don't think it actually works. There's actually a lot of friction involved, right? So the bullet will not come back down as fast as it went up either. Anyway, so the question is, when is cosine of 2 theta is 0 for what theta? If theta is going from 0 to 90. That makes 2 theta go from what? 180 degrees. So if we look at the cosine function, which is what? Cosine starts at here, and then it does like that, right? See here. Well, this would be 180. This would be 2 theta equals to. Oh, good grief. Oh, I'm sorry. I'm getting all twisted. Let me not make this more complicated than it needs to be. When is this 0 for between 0 and 180? Well, if we think about inputs to cosine of 90 is 0, right? So 2 theta equal to 90 degrees is solution. So that means theta equals to 45 degrees. That gives you the maximum range. This is not really that surprising because if you think about it, when can you make sine biggest? When sine is 1, right? How do you make sine of 2 theta be 1? Choose theta equal to 45 degrees, right? That makes the sine of 2 theta 1. And what is the max range? So we just have to plug this angle back into the formula. The max range is v squared over g. Again, there's a typo in my notes. I've forgotten to square the v in my notes, which is bad because it's dimensionally inconsistent. You need v squared over g because that gives you like meter squared over second squared divided by meter squared, meter divided by second squared, which leaves you a meter overall when you work through the dimensions here. Which, of course, is important to your physics course, but not really to this course that much, right? Now, this is almost touching up on the next topic, which is the closed interval method, all right? But we'll come back to the closed interval method is actually not a big deal. It's actually very simple. One more example of optimization, and then I'll go to the closed interval method here. So this is my example 5. And there's a problem like this in your homework. Find point on line y equals to 4x plus 7 that is closest to origin. Now, so this is my example 6.3.5 on page 225 in the notes. Now, let me just take a second here to talk about a more general question, because I think in the note in the homework, I don't think I made it a line in the homework. I think in the homework I might have made it a line. I might not have though. Look for a second here. Oh, never mind. Well, it's not. That's mission 7, so we'll get back to that when we do. But I have mission 7 in here, but it's just not handy. So what I want to say is, what if instead of this being f4x plus 7, suppose just generally that was f of x, right? And so like, there's a more general problem we could try to solve, which is you've got whatever this is, y equals f of x, right? And you're trying to find the point on the graph, y equals f of x, right? Whatever, which is closest to the origin. So if we want to find the point on this graph which is closest to the origin, what are we trying to minimize? We're trying to minimize the distance from the origin to a point on the graph, right? So basically this distance. And the point on the graph is what? It's x comma f of x, right? So the distance is the square root of x squared plus f of x, quantity squared. So that's what you'd be trying to minimize. Now, fun fact, this minimized for same x as is d squared minimized. So what I'm trying to say is the distance squared, if you want to minimize the distance, you might as well minimize the squared distance, because squared distance is like much easier. There's no square root in the squared distance, right? So when you're faced with a problem like this, my advice would be minimize the squared distance. If you don't believe me that they're the same, we'll just check this out. What's d dx of d squared? Well, it's 2d d dx. There's too many d's going on here. Maybe I should call this thing L or something. I'm going to change this to an L just so you're not buried under a mountain of too many letter D's. Call this thing L. Make our life easier. So L squared. Derivative of L squared is what? 2L dl dx, right? And, oh man. Sorry to the people who are not here. I am my own worst cameraman. Oh, there's the thing we were talking about 15 minutes ago. Sorry about that. We're now to example 5. So consider this. If L is distance, right? So it's positive. So if you think about the derivative of L squared as it relates to the derivative of L, what's the relation? Well, if dl dx is positive, then this is positive, right? If dl dx is negative, this is negative, right? So it stands to reason that if you can maximize L squared, it's the same as maximizing or minimizing L itself because of this chain rule. So my point to you is minimize the distance squared because it's easier. So, okay. Now, for our specific problem, we have 4x plus 7, right? So let me erase this here and just work on that problem. So what's the thing we're trying to minimize here is just, we want to say f of x equal to the square root of x squared plus 4x plus 7 squared. I didn't learn this. I wanted to square it, right? I can't take my own advice. So there we go. This is equal to distance from 0, 0 to x comma 4x plus 7 squared. So this is what we'd like to minimize. That's the question. Find the point on the line closest to the origin. So we can look at this f of x. To do that, we can find the critical number for f of x, which is df dx equal to 0. df dx is 2x plus twice times 4x plus 7. And why would I be wrong if I just left it like that? What am I missing? No. I mean, that might be a good idea, but the thing is, when I differentiate, I'm thinking of this as like u, right? So chain rule, 2 times u, but then times du dx, right? And du dx here is 4. So I'm missing a 4 right there before I did that. Now, if I like your idea, work it out. So this is df dx. Let's see, that's 8 plus 2, which is 10x. Oh, wait a minute. I can't do math. 2 times 4 times 4, which is what? 16 times 2 is 32. 32 plus, goodness gracious. Fine, I'll make another step. 2x plus 32x plus, so many numbers. 8 times 7, 56, right? So df dx is in fact 34x plus 56. So we set that equal to 0. negative 56 over 34, right? Oh, yeah, okay, fine. So that's what? That's minus 7 times 8 over 2 times 17, minus 1.64. Okay, approximately, right? Now, is that the closest point? Well, no. I mean, that's where the closest point is. What is actually the closest point? The point on the line is, well, minus 56 over 34, which I could simplify, I guess, if I wanted to. That's, what, 28 over 17? Sure. And then 4 times minus 28 over 17 plus 7, right? Which is approximately minus 1.64. And can you tell me what minus 1.64 times 4 plus 7 is? It's close to 0, I think. Plus 7. I mean, I'm supposed to plug this x up in here. 4 times that plus 7 is the line that we're working on. .411. Now my question to you guys is, does that make sense? That that's the closest point on the line? Could you solve this problem without calculus? I mean, I don't know. It depends on what you know, but this is 8 and this is 4. And so this has a y-intercept of about 7, right? It has a slope of 4, which means it's pretty steep, right? It's pretty steep, right? And I think I did that wrong. Well, you can't tell if I did it wrong or not, right? I made my slope slightly too steep, I think. Let's see here, I'll just try to make it a little bit less steep, just for the sake of illustration purposes. So let's see here, this is 7. And if that's 7, if you go down 8, you go 2 over. So like this point right here would be like minus 2, minus 1 for what it's worth. Because it's 2 over 1. I mean, it's 2 over means 8 down, because it's slope 4, you know? And can you guys tell me, what you can see where the closest point would be, right? You could see it. It should be from the perpendicular bisector, right? Basically. So it should be this point right here that we found. And I think you can see that that's what we found. But, you know, you'd have a hard time using pen and graph paper and ruler and getting, you know, these 2 digits, whereas it was pretty easy from calculus for us to find it. And the thing is, this same method of analysis will tell you things like, you know, you can easily replace the line with something more interesting, like, you know, you can have a parabola. And you could actually do things like, other than the origin, like suppose you want to find the closest point on the parabola to a point over here. Like suppose this point is 3, 4, for example. Find the closest point on this parabola, y equals x squared plus 2, to that point 3, 4. What would you want to minimize? In this case, you would look at the squared distance. You try to minimize f of x equal to like x minus 3 quantity squared plus x squared plus 2 minus 4 quantity squared. This would give me the distance squared from that point to a typical point on the graph. And you could set that derivative of that equal to 0, and that would find you the point on this, you know, parabola, which was closest to the point.